What's up, I'm Victor, and I'm speedrunning the synthesis of renewable copolymers. Let's jump into it. So what's a polymer? A polymer is a chain-like molecule that makes up a lot of our everyday essentials like plastics, rubbers, even the soles of your shoes, and even putty. All are polymers. Now, in order to get to a polymer, we have to start off with a monomer, which is the first building block molecule that can react with itself or other monomers in order to create a larger chain, which creates our polymer. Now, a copolymer is simply a polymer made of two different monomers. Finally, what makes something renewable? It's when the material used is able to be replenished, such as when it's derived from natural sources like plants. Now that we know the terms, let's get into the science of it. Today we're making two ABA triblock polymers in 2 steps. Now let's introduce the monomers for step 1. Here we have delta decalactone and delta dodecalactone, and we'll use this structure as a representation of either one of them. Our initiator will be 1,4-benzene dimethanol to initiate our reaction. And this reaction leads to ring opening polymerization, in where with the addition of the initiator, its hydroxyl groups will react with the monomer, allowing it to open up its ring, relieving its strain, and creating a homopolymer with hydroxyl groups on its end. This will be important for later. And with that, welcome to part 2 of our synthesis, where we turn our homopolymer into block copolymers. During this step, our monomer will be L-lactide and will be added onto the end groups of our previous homopolymer with the help of the initiator tin-2 ethyl hexanoate. The resulting product is our ABA triblock polymer. It's called this because it's got 2 of the same polymer groups that sandwich in a different polymer group, hence ABA. Before moving on to the results and characterization of these 2 polymers, let's remind ourselves how this process is renewable. Both delta decalactone and delta dodecalactone are derived from fruits and dairy products, while L-lactide is sourced from plants like corn and sugarcane. Before we get started with characterization, we have to put on our appropriate PPE for the lab. So now technically, outside of lab hours, if you have permission to, you're able to wear minimal PPE in terms of just goggles. And if you're doing reactions or doing anything with chemicals, obviously you're gonna wear gloves, right? But you don't have to wear a lab coat, but I am for the purposes of this video. But I don't have any gloves on because I'm not doing any chemistry. Anyways, welcome to the FTIR. Fourier transform infrared. And all this does essentially is you load your sample onto the little stage here, you clamp it. There's a small little diamond or another material that's really refractive, and it shoots infrared rays at it, and the resulting transmittance or absorbance, depending on which you choose, shows up here as your results. The results for our samples should look like this. Boom. All right, here we're at the DSC. It stands for differential scanning calorimetry. And in this instrument, we load our sample into little pans, and we heat them up really, really hot. For the purposes of this experiment, we're going from -50 Celsius to 250 Celsius. So not too hot, but still pretty hot, especially if you touch it with your bare hands. And it shows us important things like its melting temperature, its glass transition temperature, and its crystallization temperature. There are some rooms that don't allow you to bring in your PPE from the lab. This room being one of them, where it holds the NMR, our next instrument that we're using. It stands for nuclear magnetic resonance, and all it is in a nutshell is a really strong magnet that analyzes the relationship between, in our case, the hydrogen atoms of our sample and its relationship to the magnetic field that was created by, well, the magnet. And our data looks like this, and every peak represents a group of hydrogen atoms. And with this, we're able to find out what our molecular structure looks like. So what did we learn today? Today, we successfully synthesized and characterized not 1, but 2 ABA triblock copolymers that were synthesized via ring opening polymerization, which is a derivative of chain growth, polymerization, and we were able to characterize them via FTIR, DSC, and NMR, which allowed us to find their molecular weight, composition, and other important details like glass transition. And future work might include things along the lines of different combinations of lactones, because different combinations have different properties. And so, depending on what you are using them for, you might need a different combination of monomers to create your block copolymer. And as always, be safe when you're doing science